quotes that began a book, but it's the initial mystery that attends any journey is how did the traveler reach its starting point in the first place? And I think that's perfectly appropriate for the Origins program here and the one that I run. But really, if one thinks about mysteries, it's getting to the beginning that's the really important part. And the mystery of our universe and getting to the beginning of what is, in fact, one of the greatest mysteries around right now in science is what I want to get you to today. So we'll get there. But we will do it by addressing this question that's been around for as long as people have been around. Why is there something rather than nothing? And people have asked that question, as I say, as soon as they could ask questions. And there's lots of different ways of answering it. You can just you can write in the beginning and then have a whole book that doesn't explain anything about anything. And or you can actually turn to the universe and try and figure out the answer. And that's what I want to talk about, and the fact that the universe is giving us answers that we, as was mentioned in that interview with Krista Tippett, that humans would never have come up with. Our imaginations pale in comparison to the imagination of the universe, which is why we have to keep looking. This is a Hubble Space Telescope picture, the Hubble Deep Field, and like all Hubble Space Telescope pictures, it's my favorite one. But in this particular picture, every dot is a galaxy, not a star, and there are 400 billion galaxies in the observable universe. And when I look at pictures like this, it does inspire my imagination, because many of these galaxies, especially the small dark ones there, are maybe up to 10 billion light years away, and that means that light left them 10 billion years ago, and well before our Earth and Sun formed. And therefore, most of the stars in that picture are dead now, and any civilizations that may have existed around them are dead as well. And if they take the picture and look at us 10 billion years from now, we'll be long gone and forgotten as well. And so these kind of things are inspiring, and that's what I want to do, to inspire the actual understanding of the universe. That's really, if you read the poem at the beginning, it's the universe. One of the points I want to make is that the universe doesn't exist so that we can be happy, and we just have to get over it, and we should take it for what it is and learn from it. So that's what I'll try and do now. Following Henrietta Leavitt was this guy here, who I'm going to praise for a different reason, although he used much of her work. This is one of my heroes, Edwin Hubble. And he's one of my heroes because he gives me great hope for humanity, because he began life as a lawyer and then became an astronomer. And so there's hope for many of the Harvard students in this audience. So Hubble did many things, but he really was the first one. The thing that is aside to what I want to talk about, but I'll mention, with the Mount Wilson telescope in 1925, he changed our picture of the universe in a very important way. Just think about it. A single human lifetime ago, 88 years ago, the universe consisted of one galaxy surrounded by an eternal vast empty void. Okay, that's a single human lifetime ago. Now we know there are 400 billion galaxies in the observable universe, and the universe is expanding. I mean, everything has changed, so it's not surprising that we're surprised. We're like the early map makers, just beginning to understand the universe on larger scales, and what we're learning is amazing us. But he was actually the first one to demonstrate that there were other galaxies. Up to that point, when you look through telescopes that were then existing, you saw these fuzzy things called nebulae, which is Latin for fuzzy thing. And with the telescope, he was able to, the Mount Wilson telescope, to see that these were in fact other island universes, other galaxies. So until that point, one galaxy, now 400 billion. But then, of course, he made the discovery that we all remember him for. He discovered that the universe is expanding. By using this data, he made it clear that the universe was expanding. So well, let's just heuristically see what he saw. There are a lot of biologists here, but these are not sperm, these are galaxies. And what schematically he saw is, as we look out, one of the most amazing things is that galaxies on average are moving away from us. And objects that are twice as far away are moving twice as fast, and 3 times as far away, moving 3 times as fast, and so on. And so when you see this, immediately you know what it implies. It means we are the center of the universe. It's obvious when you look at it. And it certainly seems that way, but as many of my friends remind me on a daily basis, that's not true. It means the universe is expanding. And the problem with this is, I've thought of a lot of different ways to try and show this, and the problem is that we live in our universe. Well, most of us do. The Republican Party doesn't, but the rest of us do. And so we have this myopic picture. To really understand that this implies that the universe is expanding, we'd have to get outside of our universe. Not so easy to do, but it's easy to do for a universe you can draw. And here's a two-dimensional universe I can draw on a screen. So these are galaxies I put down at regular intervals. And you can see that at time t1, this region is smaller than at time t2. So if you're standing outside of it, you can see that it's expanding. So that's clear. But what would you see if you lived in that universe? Well, quite simply, just pick a galaxy, any galaxy, to see what you'd see. We can superimpose this image on top of this one, placing this galaxy on top of itself. And what we see is exactly what Hubble saw. Every galaxy is moving away from this galaxy here, and those that are twice as far away have moved twice the distance at the same time. Those that are 3 times as far away, 3 times the distance, and so on. And it doesn't matter what galaxy you pick. You see the same thing from every galaxy. So this means that it depends on how you like to think of things. Either there is no center of the universe, or every place is the center of the universe. It doesn't really matter. What it really means is that the universe is expanding. And that changed everything, because once the universe was expanding, it meant, first of all, working backwards, the universe had a beginning, the Big Bang, which we now know is about 13.8 billion, well, except for in Arkansas and Ohio and a few other places. It's 13.8 billion years ago. And of course, it also means that if the universe is expanding, the central question of 20th century cosmology then became, will that expansion end? Will the universe end with a bang or a whimper? Will the expansion go on forever, or will it stop? And in fact, actually, as someone who's trained as a particle physicist, the reason I got into cosmology was because I wanted to be the first person to know how the universe would end. It seemed like a good idea at the time. And you'll see my reasons were all wrong. But in any case, so that not only had profound significance, of course, for science, but also, obviously, for religion and theology. The beginning of a universe meant, well, what may have happened before the beginning and how did it begin, etc. And we'll try and address those questions. Now, in order to know how the universe would end, and the reason, as I said, I got into cosmology, it's quite simple. Einstein told us the remarkable fact that space is curved in the presence of matter and energy. And that means that space, the geometry of space, can be interesting. And in fact, in 3 dimensions and in 2 dimensions, there are 3 possible geometries, so-called open, closed, or flat. It's very hard to draw curved 3-dimensional universes because we're 3-dimensional beings, so we couldn't picture them. But I can draw 2-dimensional universes, so these are just guides for the eye, but as with 3 dimensions, there are just 3 types, open, closed, or flat. And a closed 2-dimensional universe is the surface of a sphere, for example, and a flat 2-dimensional universe is a flat piece of paper. While one can't draw them in 3 dimensions, similar things would be true. In a closed 3-dimensional universe, if I looked far enough in that direction, I would see the back of my head. Light would go around the universe. And a flat 3-dimensional universe isn't flat like a piece of paper, but instead is flat in the sense that it's a universe you always thought you lived in, and the one where the x, y, and z axes always point in the same directions, and light travels in straight lines. And the big question of 20th century cosmology was, which universe do we live in? Because it would determine our future. Because if you have a universe full of matter, and it's closed, it will expand, stop, and contract in a big crunch to reverse the Big Bang. Whereas an open universe will go on expanding forever, and a flat universe is the boundary between those two. It will slow down but never quite stop. So when we determine the geometry, we figured we'd know the future. So, since to determine the geometry requires knowing how much mass and energy there is in the universe, all you have to do is weigh the universe. It's really quite simple. And that's taken us many years. I wrote a whole book about it, in fact, but a single picture, in fact, nowadays will do the job. But before we get there, I want to take you back for some historical perspective, especially for the young people, to 1936, Science magazine. Many of you young people will become scientists, and you'll submit articles to Science, and you'll be rejected. And the point I want to tell you is that it used to be kinder or gentler. It was just easier back then. And I want to show you. So this is an article from 1936. The title is "Lens-like Action of a Star by the Deviation of Light in a Gravitational Field." But here's how it begins. Some time ago, R.W. Mandel paid me a visit and asked me to publish results of a little calculation which I had made at his request. This note complies with his wish. Okay, try that today and see what happens. Okay, see if you get in. Now, the author had credentials, because he was Albert Einstein, so it was okay, maybe that helped. But what he published was something he thought was very unimportant. is he had shown that light bends in a gravitational field, but if there's a large enough mass, clearly, if you put a large enough mass and you have a light source behind it, the light rays can bend around it and converge and come back together again and be magnified, like my glasses magnify nearby objects. Or if I had a cut glass goblet here and I looked at all of you, I'd see many images of all of you. So he realized that space can act like a lens, but he thought it would be unobservable and very unimportant. So actually, here's his notes from 1936, from his notebook. And the interesting thing is, it was so unimportant that he forgot that in 1912, if you look at his notebook, exactly the same calculation. He forgot he'd done it. He just didn't think it was important. And my favorite part of this is his letter to the editor after it was published. He wrote, "Let me thank you for your cooperation with the little publication which Mr. Mandel squeezed out of me. It is of little value, but it makes the poor guy happy." That's how science is done. Okay? Well, it wasn't of little value because it allows us to weigh the universe. And here's a picture of what Einstein said would never be observed. This is gravitational lensing. This is a cluster of galaxies. Clusters of galaxies are the largest bound objects in the universe. So if you can weigh them, you can weigh everything. Okay? So if you can weigh these guys, you can weigh the universe. And they're so large, they're maybe 10 million light years across. They contain many, many galaxies. And this is a picture of a galaxy located 5 billion light years away. Again, every dot in the picture is a galaxy, not a star, each containing maybe 100 billion stars. But you don't have to be a rocket scientist to see that in this image, there are these weird blue things that look different. And what they are multiple images of a single galaxy located 5 billion light years behind that cluster. One that might not even be observable if it weren't magnified, but it's magnified and distorted and they have multiple images. So this is proof, this is evidence of the fact that space is a lens. It's curved around matter and it can lens things, which is wonderful. But of course, we understand general relativity, and so we can use it. We can say, well, how much matter would there have to be in this system, and how is it distributed in order to produce this image? It's a complicated mathematical inversion, but you can do it. And when you do, you get a picture like this. The spikes are where the galaxies are, but you notice that most of the mass in this system is where the galaxies aren't. There's a huge mountain of mass, almost 40 times as much mass in that image as meets the eye. In fact, around each galaxy, there are mountains of mass that don't correspond to visible light. Most of the mass in these systems, and indeed in all such systems, doesn't shine. And physicists were so creative, we call it dark matter. It doesn't shine. And the interesting thing, if you're a particle physicist, is that there's enough of it, there's so much of it, at least 10 times more of it, than can be accounted for by protons and neutrons, the stuff that makes us up and everything in this room up. We know how many there are for different reasons, and there's far more dark matter than can be accounted for by protons and neutrons, so we're virtually certain it's a new type of elementary particle, which makes it exciting because it means it's not just out there, it's in this room, going right through your bodies as you nod off during this lecture. And that means we can do experiments here to detect it. And that's of great interest, and there are experiments around the world, some of which actually I proposed many years ago, and I was going to go into them, but I think I'm not going to in order to save time given the length of the introductions. But so it doesn't really, it's a fascinating, if we detect it, we'll learn what the nature of most of the mass in the universe is, and most of it isn't us. But for this purpose right here, we don't have to care what it is, we just have to care how much of it there is. And this kind of image, adding up matter in these kind of systems, has finally allowed us to answer the question of how much stuff there is there in the universe, weighing the universe. And so I'll do a drum roll. Okay. And the answer is, ta-da, see, there are people in the back fainting, I can see. In physics, whenever one has an important number, one gives it a Greek letter to sound scholarly. And omega here is the ratio of the amount of stuff, the amount of matter in the universe, the actual amount of matter, divided by the amount you'd need to make a flat universe, an exactly flat universe. So if it's less than 1, the universe is open. If it's greater than 1, the universe is closed. If it's equal to 1, the universe is flat. And you can see with this and many subsequent measurements, it's now definitively known that by a factor of 3 or so, there's 3 times too little matter to make the universe flat. So the universe appears to be open. We've answered the Holy Grail. It's all done. But there's a problem. Because we theorists knew the answer. We always know the answer. We're not often right, but we always know the answer. And we knew that we lived in a flat universe because it's the only mathematically beautiful universe. And the observers were doing what they do so well, which is getting it wrong. And of course, the problem is this is a difficult thing to do because it's a very indirect way to measure the geometry of the universe, after all, because you try and add up the amount of matter in the universe, and you plug it in Einstein's equations and try and measure the other terms, and you put it all together and you try and measure the curvature. Wouldn't it be better to measure the curvature of the universe directly? And it is amazing that in the last decade or so, we can now do that. We've been able to measure the curvature of the universe directly. And to figure out how to do it, let's ask the question, how could you measure the curvature of the Earth if you couldn't go around it or couldn't go into space and see that the Earth was round? It's really simple. You draw a triangle, and then you ask a European high school student or a Harvard undergraduate, what's the sum of the angles in a triangle? And it's 180 degrees. Okay. Where you came from, they know those things. Okay. But that's because you learned your geometry from Euclid. On the surface of a sphere, it would be quite different. On the Earth's surface, I could draw a triangle this way. I could go across the equator, make a right angle, go up 90 degrees to the North Pole, and then another right angle back down to the equator, and now I have a triangle with 3 right angles. 3 times 90 is 270. So literally, if you were able to draw a big enough triangle on the surface of the Earth, you would be able to show the Earth was curved. Now, it is remarkable that exactly the same thing is true for even 3-dimensional curved spaces. If you were to draw a big enough triangle, you could measure the curvature of the universe. And people have tried for hundreds of years to do that, but we now have been able to measure a big enough triangle. And we use what is perhaps one of the most important observations in cosmology, the cosmic microwave background radiation, the afterglow of the Big Bang, discovered in New Jersey, of all places, in 1965, by 2 people who didn't know what the hell they were doing. But they won the Nobel Prize anyway. Because you really don't have to know what you're doing to win the Nobel Prize. Forgiven to at least one Nobel laureate I know in the audience. But you just have to discover something important, and they did. They discovered the afterglow of the Big Bang. And here's what it is. So when we look out at the universe, we're looking back in time. We're doing cosmic archaeology. When we look at galaxies that are 1 billion light years away, 1 billion years back in time. So if the universe is 13.8 billion years old, you'd think if you look out far enough, you'd see the Big Bang. And in principle, you could, except between us and the Big Bang, there's a wall. Not a physical wall like this, but effectively like the one in this room, because I can't see past this wall because the wall's opaque. If I look out at an early time, the universe was hot enough, before about 100,000 years or so, it was hot enough that neutral matter couldn't exist. Hydrogen was broken apart into its protons and electrons, and it was a plasma, and it's opaque to radiation. So you can't see an electromagnetic radiation back before that time. But then the universe cooled down, matter became neutral, and just like this wall, which I can see because the air is transparent between me and the wall, space became transparent. And one of the predictions of Big Bang is that I would see radiation coming at me from all directions from that so-called surface of last scattering. And because the universe has cooled since that time, it's no longer 3,000 degrees, but 3 degrees, and that's what they discovered in New Jersey. Now, this is such an important image that if you took a picture of this, you'd get a baby picture of the universe. Another Nobel Prize has been given that picture. I'll show you 2 versions of it in a minute. But from our perspective, what's really important is that there's one scale on that baby picture, and it's 1 degree. And that's because 1 degree represents about 100,000 light years. Now, Einstein told us no information can travel faster than light. And therefore, anything that happened over here on this surface can't affect anything over there, because light can only travel this far in 100,000 years. And that means if you're a lump of matter, say this big, you start to collapse like lumps do and heat up and do all sorts of neat things. But if you're a lump of matter that's this big across, you don't even know you're a lump, because gravity travels at the speed of light. So it's like Wile E. Coyote when he goes off the cliff in those cartoons. He sort of hangs around for a while before he knows he's supposed to fall. Lumps that bigger than this size don't collapse. So if we could image this surface and look at the lumps and ask how big are they, we could get a sense of, in fact, the largest lumps that would collapse due to causality. But that gives us a triangle, you see, because it's a ruler of a known length, a given distance away. And you see, in a flat universe where light rays travel in straight lines, that 100,000 light year across ruler will subtend, say, 1 degree on our eye. But in an open universe, as you go back in time, light rays diverge as you go back in time. So the same ruler will look smaller, maybe half a degree. And in a closed universe, light rays converge as you go back in time. And so the same ruler will look bigger, maybe 2 degrees. So all you have to do is take that picture and look at the lumps and ask how big are they, and just by causality, you'll measure the curvature of the universe. And so we can do that. And this was one of the first experiments that did that. This is the boomerang experiment. It was a balloon and a microwave radiometer. It was sent up in Antarctica and went around the world, which is easy to do in Antarctica, actually. If you're in the South Pole, you just do this. But it was a McMurdo. So it took 2 weeks to go around, came back to where it began, called the boomerang experiment for that reason. And it imaged a region of the microwave sky. And this is superimposing the original picture. This is the picture. This is a false color image. These are the lumps. This is the hot spots and cold spots in the microwave background. This is an amazing image. It is a baby picture. These are the lumps input at very near the beginning of time that would later on collapse to form all the stars and galaxies and planets and aliens and everything that's in the universe today. It is really remarkable to see this primordial picture. But again, for our purposes, the question is, how big are those lumps? Okay? And we can do that, but I should show you at least a more recent picture. This is, as you've probably seen in the press, there have been several satellites that have gone and looked at the full sky, and this is a picture from the what's called the Planck satellite that just published results, and this is the full sky. This is a galaxy. Get rid of the galaxy, and then you can more clearly see these are these primordial lumps that would later on form all the galaxies and structures we see today. The question is, how big are they? So to see that, we can take, this is the boomerang image at different false colors, but we can create universes on computers. And we can lay down 100,000 light year across lumps on average and ask how big they look. So in a closed universe, an open universe, or a flat universe, and in a closed universe, the average 100,000 light year across lump should look that big, but that's bigger than these lumps. In an open universe, the average 100,000 light year across lump should be about that big, but that's smaller than these lumps. But just like Goldilocks, in a flat universe, it's just right. And we now know today, to an accuracy of better than 1% almost, that the universe is flat. We finally know the universe is flat. So the first thing we do is this. But we don't do that, okay, because because there's a problem. Just a few minutes ago, I showed you the universe was open. There's only 30% of the amount of stuff needed to make a flat universe, but the universe is flat. So where could the other stuff be? Well, if it isn't where the galaxies are, it's got to be where the galaxies aren't. But what's where the galaxies aren't? Nothing. And that's the first clue that nothing is interesting. Because nothing, as was just pointed out earlier, is actually a very interesting thing in modern physics. Empty space is a very fascinating object because it's really a boiling, bubbling brew of virtual particles popping in and out of existence in a time scale so short you can't see them. Now that sounds like religion, or kind of counting angels on the head of a pin, inventing things that you can't see. It would be. You can't see them directly, but due to the laws of quantum mechanics and relativity, they have to be there, and moreover, we can see their effects indirectly. And that's really important. In fact, I have a picture here, an animation. This is an actual animation based on a real calculation of what the space inside of a proton looks like. Okay? In fact, it was shown at the Nobel Prize ceremonies by the people who first allowed this calculation to be done. And you can see that, and if you went to a good high school, you learned that protons are made of 3 quarks. But we lied. Okay? They're made of 3 quarks, but if you add up the mass of those quarks, they only add up to about 10% of the mass of a proton. Most of the mass of the proton comes from these particles and fields that are popping in and out of existence in a time scale so short you can't see them. And that's remarkable. So we know they're there, and we can actually calculate their contribution to the proton now and to elementary particle masses. And that's a remarkable success. Well, emboldened by that success, we can try and use the same physics, and if you can calculate the contribution to the energy inside a proton, surely we then try and calculate the contribution to the energy of the universe. And so we can try and calculate the energy of empty space. And when we do that, we come up with the worst prediction in all of physics. Okay? We come up with the prediction that the energy of empty space is roughly a gazillion times the energy of everything we see. And that is the worst prediction because, in fact, we know it can't be much more than what we see or we wouldn't be here. Yet we predicted naively that it's about 120 orders of magnitude larger. And this problem's been around since I was a graduate student, since I was here in Boston. And we never talked about it because it was so important. It's called, but again, it wasn't a problem because we theorists knew the answer. We always know the answer. We knew it was 0. Knew the energy of empty space had to be zero. It's the only sensible value, because if it wasn't, let's say it was comparable to the energy of everything we see, then you'd have to cancel this big number to 120 decimal places, leaving some non-zero number in the 121st decimal place. But we don't know how to do that in physics. No one knows how to do that. But it's easy to get zero. Mathematical symmetries can produce zero, equal and opposite things that cancel exactly. So all of us theorists knew the answer. We knew there was some new symmetry of nature we hadn't yet discovered, but we would, that would one day explain why all those things canceled and you get exactly zero, and we could go home at night and sleep. But, as I pointed out at the beginning of this lecture, the universe doesn't care what makes us happy. It's not sufficient to say that's the only sensible thing. Cosmology is a science, and therefore you have to go out and look. So how can you determine the energy of empty space? Well, remarkably, Einstein tells us something wonderful. All of the physics students here know that gravity sucks, okay? It always pulls, it never pushes. But if you put energy in empty space, it blows, okay? It produces a kind of cosmic anti-gravity. You put energy in empty space, and the equations of general relativity tell you it must be gravitationally repulsive. So if you were to measure the expansion of the universe, as Mr. Hubble did based on Henrietta Leavitt's data, measuring the velocity of objects versus time, this is a Hubble plot nearby, then the idea is you can look to see, and a sensible universe should be slowing down. But if you put energy in empty space, it'll speed up. So how can you do this? Well, it means you have to measure distances and velocities, not just nearby, but across the whole universe, okay? And to do that, how do you measure distances that are from objects that are so far away? Well, it's very, very difficult because we don't have tape measures that are that long. You need something we call a standard candle, something whose intrinsic brightness we believe we understand, and then you look at it through a telescope, you see how bright it looks, and therefore you determine the distance to objects. And it's taken a long time, and much of the last century, to come up with good standard candles, but we have come up with a good standard candle, and here's a picture of one. This is a galaxy long, long ago, far, far away. Actually, not that far away. It's only 70 million light years away. And it's a spiral galaxy, much like our own. Once you've seen them, you've seen them all. My apologies to astronomers. In the center of the galaxy, there's about 100 billion stars here. The center of the galaxy contains maybe 10 billion stars. And here is a star shining with a brightness of 10 billion stars. How could that be? Well, there's two possibilities. One, it could be a star in our galaxy that got in the way of the picture, which is reasonable to assume. But it isn't. It's a star at the edge of that galaxy shining with a brightness of 10 billion stars. Why? Because it's a star that's just exploded, a supernova. And supernovae are the brightest cosmic fireworks in the universe. When they explode for a period of a month or so, they shine with a brightness of 10 billion stars. Now, fortunately for us, stars don't explode too often. But fortunately for us, they explode. Fortunately for the projects we're involved in here and at ASU. Because you wouldn't be here if they didn't explode. Because all the important elements that make up your body were created in stars. In the Big Bang, the only things that were created were hydrogen, helium, and a little bit of lithium. But the important stuff, well, for some people here, lithium may be important. But for the rest of us, carbon, nitrogen, oxygen, iron, all those things are created only in the nuclear furnaces inside stars, and the only way they could get into your body is if the stars were kind enough to explode. So you are literally stardust. It is the most poetic thing I know about the universe. I wrote a whole book about it. You are star children. You are intimately connected to the cosmos in ways that you might never have imagined. In any case, the problem is they don't explode too often. They explode about once per 100 years per galaxy. So if you want to study these objects as standard candles, how do you do that? Once per 100 years per galaxy. Well, it's quite simple. You assign a graduate student to each galaxy. Okay? 100 years is about right for the PhD, and as we all know, graduate students are cheap, so they die, you just get a new one, it's no problem. But you don't have to do that. Because the other amazing thing about the universe is that it's big and it's old, and rare events happen all the time. So tonight, if it's still clear, and you hold your hand up and hold a dime-sized hole, and look at a region of the sky where there are no stars. With one of the largest telescopes on Earth we have down in Chile, say, if you looked at that region of the sky where there are no stars, dime-sized region, you'd see about 100,000 galaxies. And if you work it out, once per 100 years per galaxy, 100,000 galaxies, on a given night, you're going to see a few stars explode. And observers do that. They apply for telescope time. They see stars explode, and as a result, we can measure exploding stars in many cases and follow them over the period of a month while they're bright. This will go over again. There's the star. It's going to explode. This is brightness. We can measure its colors, and from its colors, we can determine what kind of supernova it is. There are different types. This is called type 1a. And it turns out to be a wonderful standard candle. So wonderful that you can use it to measure the distances in galaxies in which these supernovae exist. But since they're so bright, you can measure them across the universe. And in 1998, two groups of astronomers who really didn't know what they were doing were trying to measure the rate at which the universe was slowing down. And they were able to measure, this is the new Hubble curve, this is nearby stuff. And the big question was, does this curve upwards or downwards? They were looking to see how fast it curved downwards. And to see what happens here, you just draw a straight line through that data set, bring the whole thing horizontal. And what they expected to see was how well these supernovae were following this curve, which is a universe that's slowing down. But much to their surprise, these supernovae didn't even lie on the straight line, but above the straight line. And there's only two ways to explain that. One, the data's wrong, which it usually is. Or two, the expansion of the universe is actually speeding up. And just for fun, if you try and fit that data and ask how much energy would you have to add to empty space to fit the data, you need exactly what we're missing. If you put 70% of the energy of a universe, of a flat universe, in empty space, everything fits together. And these people won the Nobel Prize for that discovery. So here we have the current picture of the universe that I want to use our starting point for talking about the future and trying to ask where we came from. This is a universe in which 70% of the energy in the universe resides in empty space, and 30% almost resides in dark matter, and 1% or so resides in everything we see. So we are just a bit of cosmic pollution in a vast sea of dark matter and dark energy. You get rid of us and all the stars and all the galaxies and everything we see in the night sky, and the universe would be largely the same. So much for a universe that's made for us. But the other thing is, and there's two lessons I want you to draw from this lecture, and the first one now is very important. You are far more insignificant than you ever thought you were. Okay? That's the first takeaway lesson. That's you, not me. No, all of us are far more insignificant than we ever thought. Okay, but let's summarize then. So the dominant energy in the universe resides in empty space. We don't have the slightest idea why it's there. And if someone here comes and gives a lecture next year and says they know why they're lying, especially if they're a string theorist, okay? And its existence is probably tied to the beginning of space, and more importantly, as you'll see, it will determine our future. Okay. So, in fact, when we talk about determining the future, I want to go back to say why I got into this, why I thought we could determine our future from measuring the curvature of the universe. And I want to take you back to your favorite time, high school physics. Now, you may remember, and that we teach you how, if I take a coin, which I don't have, I do have a foreign coin here somewhere. I just came from Norway. I have a coin. I think I have a big coin. Yeah, okay, Sweden. Anyway, and I throw it up, it comes back down. If I throw it up faster, it comes back down. If I throw it up really fast and there's no ceiling, it doesn't come back down at all. And we teach students how to calculate that by turning that problem into bookkeeping. Because we say the coin has energy, and it has two bits of its energy. A so-called positive piece, the kinetic energy, and a negative piece, the potential energy. The positive piece comes from motion, the negative piece comes from the mass of the Earth and gravitational attraction. But what's really neat is that we then, it just becomes bookkeeping. If this term beats that term, the coin will escape. If that term beats that term, the coin will fall back down. So if the total energy is positive, it escapes. If the total energy is negative, it comes back down. Well, the really neat thing is in a universe full of matter, you can do the same thing. Let's just take Hubble's picture here, and we're at the center. And if the universe is the same everywhere, then what happens to every galaxy will happen to any galaxy. So to calculate the future of the universe, you just have to calculate the future of the motion of any galaxy. Say, take this one. And then it's just the same as for the coin. To determine whether it'll go on expanding forever, we just calculate its total energy. And the positive piece comes from its motion, but Mr. Hubble and Henrietta Leavitt told us its motion. The negative piece comes from the mass of all the stuff in the region pulling it inside, which includes dark matter. So we calculate that. And so if the negative piece beats the positive piece, if B over A is bigger than 1, this region will collapse. If B over A is less than 1, so the positive piece beats the negative piece, it will go on expanding forever. And the really neat thing is, it turns out B over A is nothing other than this quantity omega. And I I remind you, we've measured omega. Omega is 1. We live in a flat universe. And if omega is 1, then B is equal to A. And if B is equal to A, then the negative piece equals the positive piece. But if the negative piece equals the positive piece, then the total gravitational energy of every object in the universe is 0. Now, if you wanted to make a universe from nothing, what would you make the total gravitational energy? So this begins to suggest that maybe we can create a universe from nothing without any supernatural shenanigans. And what I want to argue is we absolutely, in principle, can. Can we prove our universe came that way? No. But I want to discuss that now in the last few minutes of the talk. First of all, I've learned that one has to be careful when you talk about nothing. Because, as I said in the book, and it infuriates some people, philosophers and theologians are experts at nothing. And they get upset if you don't talk about it in the way they'd like. So I want to talk about the 3 different versions of nothing. The first version, just empty space, the nothing of the Bible, the vast cosmic void. Well, it turns out that nothing is unstable. Because that nothing, I remind you, is a bubbling, brewing sea of virtual particles. Well, those aren't real particles. If you try and measure the particles in empty space coming from this way, you won't see anything. There aren't any real particles. But if you allow gravity into the mix, then there can be a gravitational attraction between the particles, and that can produce a negative energy component to their total energy. The reason virtual particles pop in and out of existence so quickly is they carry energy. And if they existed for a long time, they'd violate energy conservation, so they have to disappear, according to the Heisenberg uncertainty principle. But if I put gravity in the mix, then I can make the total gravitational energy, total energy of these particles 0. And if that's the case, they can exist with impunity. And quantum mechanics says fluctuations will happen all the time. So if you allow gravity into the mix and you have empty space, you are guaranteed, if you wait long enough, particles will be spewed out. So in fact, that kind of empty space is unstable. The big question would not be, why is there something rather than nothing, but why is there nothing rather than something? But if there were, we wouldn't be here to ask the question, so that kind of nothing, easy to get rid of. Automatically, you can make enough stuff to account for everything you see. But you might say, that's not nothing, because you've got no particles, you've got no radiation to start with, but we've got space. Where did the space come from? Well, if we have a quantum theory of gravity, I remind you, general relativity is a theory of space and time. And the big question is, can you make it a quantum theory? We don't know for sure. But if it was a quantum theory, if it is a quantum theory, then space and time become quantum mechanical variables. And I remind you, in space, because of quantum mechanics and relativity, particles will pop in and out of existence. If space and time are quantum mechanical, then spaces and times can pop in and out of existence in a time scale so short we can't see them. So once you make gravity a quantum mechanical theory, you are guaranteed that whole universes, spaces that did not exist, can pop into existence and out of existence. Virtual spaces can pop in and out of existence. Now, if I create a whole space that has 0 energy, it doesn't have to pop out of existence for it, okay? So now it's sounding like there's a grand synthesis in the air because I told you the gravitational energy of every object in the universe is 0, but it's not that simple. Because the only universe in which we can mathematically show that it has 0 total energy is a closed universe, not a flat universe. And we don't live in a closed universe, so what gives? Well, the point is that most closed universes, as I told you before, a closed universe will expand, stop, and contract if it's full of matter. And these microscopic closed universes will expand and contract in a timescale so short, it'll be microscopic timescales. The only way you could have a closed universe that would survive long enough for us to ask the question is if you put energy in space in that closed universe. That would cause that closed universe to puff up and not collapse. Well, remarkably, that's just what particle theory predicts. And Alan Guth, who's in the audience, was the first one to predict it. Given what we know about particle physics, we have every reason to believe that, in fact, at early times, there was a vast energy stored in empty space that caused our universe to expand potentially exponentially in a very short time. In fact, in a time frame of a millionth of a billionth of a billionth of a billionth of a second, the universe could have expanded by a factor of 10 to the 90th. It sounds like science fiction. But we don't think it is, because it turns out that not only does that, in fact, explain various general properties of our universe. But if you look at that baby picture of the universe that I showed you with those lumps, quantum mechanical fluctuations during inflation will produce lumps that look just like the lumps that are seen up there. So we have great reason to believe that inflation actually happened. But that does just what we need. Because if you have inflation, like blowing up a balloon, when it gets very big, it looks flat. The Earth looks flat in Kansas. I just flew over it yesterday. And so the only closed universe that could survive long enough for life to evolve on this planet is one that looks flat because of inflation. So, what this tells us is, if you wanted to create a universe from nothing in which there was no space, now I repeat, no particles, no radiation, no space, no time, what would the properties that universe would have? It would have the properties just like the properties of the universe we see today. Now, does that tell us it had to happen? No, it doesn't. Of course it doesn't. But it tells us it's plausible. And that, to me, is an amazing thing. There are several eminent biologists in the audience here, and they know that before Darwin, life was a miracle. Every bit of life was specially designed for its environment. Okay? But Darwin showed that it was plausible, given genetic variation and natural selection, that you could produce a complete diversity of life on Earth without any supernatural shenanigans. Okay? And it was plausible. He had some evidence on the basis of what he saw, but he didn't know about DNA, he didn't know about the details of genetics. Well, we're at that situation now. We don't have a quantum theory of gravity, but what we know is based on what we know. It's plausible. You don't need anything supernatural to create everything we see from nothing. Now, some people will say, of course, that's not nothing, because you have no particles, no radiation, no space, no time, but where did the laws come from? Surely for that you need God. Okay, well, this is what I just said. It turns out the laws of physics, we now think, may themselves be accidental. And to show you that, I'm going to show the last slide that requires any thinking. Okay. This is a brief history of the universe, brief history of time. This is the density of matter in the universe as the universe expands. It goes down as 1 over the volume. The energy density of empty space remains constant, and we live right here, when the energy of empty space is about 3 times the energy density of matter. But if you stare at this long enough, you go crazy, particle physicists have in particular. Because you look at that and you say, there's something wrong with this picture. We live at the only time in the history of the universe when these two numbers are about the same. At all earlier times, the energy of empty space would be much less than the energy of matter. At all later times, the energy of empty space would be much greater. Why do we live 13.8 billion years? Copernicus told us it isn't supposed to be that way. There's no combination of fundamental parameters in physics and particle physics that give 13.8 billion years. It shouldn't be special. So there's some problem here, and physicists have suggested a solution. It's quite simple. Galaxies exist. Why? Well, let's say the energy of empty space was 50 times bigger. Then these curves wouldn't cross here, they'd cross there. But what time is this? This is the time when galaxies first formed. But the energy of empty space is gravitationally repulsive. If it dominated over the energy of matter before galaxies formed, galaxies wouldn't form. The repulsive force would beat out the attractive force. There'd be no galaxies. And the first person to suggest that was Steve Weinberg. Maybe this is telling us something. This has led to what I've called anthropic mania. If there are many different universes, and let's say the energy of empty space is a random quantity, there's no fundamental physical reason it should have any value, and it varies in each one, then only those which is not much greater than what we measure today will galaxies form. And only then will stars and planets form, and only then will astronomers form. So the universe is the way it is because there are astronomers here to measure it. It sounds very whatever, solipsistic to say the least. It sounds like a tautology. It also sounds religious. But it's none of those. It's more like natural selection. It's like cosmic natural selection. We would be amazed to find ourselves living in a universe in which we couldn't live. I mean, that would be worth writing about. Okay? So it's not too surprising in this case. And it's pretty depressing, though, if it's true, because it means this fundamental parameter of the universe is an accident. Now, you see, particle physicists have jumped on this, because particle physics is way ahead of cosmology. Because in cosmology, there's one number we haven't understood for a long time. In particle physics, there's many more numbers we haven't understood for much longer. We don't know why. gravity is the weakest force in nature. We don't know that the proton's 2,000 times heavier than an electron. We don't know why there are 3 generations of elementary particles. A lot of things we don't know. But particle physicists have jumped in the sense that maybe we don't have to understand anything. Maybe it's all an accident. And then you don't need a theory of everything. You just need a theory of anything. And we have such a theory. It's called string theory. I'll give you a one-page summary of it. One guy says to another, I just had an awesome idea. Suppose that all matter energy is made of tiny vibrating strings. And the second guy says, okay, what would that imply? The first guy says, I don't know. So that's the history of string theory in the last 40 years. Because string theory used to be a theory of everything because we hoped it would give a unique theory of everything. But in fact, it was realized early on, of course, that in order to be consistent, you need lots of extra dimensions. But we don't see those extra dimensions. So you have to get rid of them. And the standard way is to curl them up and so small you don't see them. But each different way of curling up those extra dimensions produces a different three-dimensional universe with different laws of physics, which used to be a problem. But every wart in string theory becomes a beauty mark. Now it's a landscape. Because now you could imagine maybe 10 to the 500 different universes, and they collapse in different ways in the extra dimensions. Some of them form 3-dimensional universes, some of them form 2-dimensional universes, but one of them is bound to look like ours. And therefore, maybe the reason we're in it is because we can be in that one. Now that is pretty depressing, really, because it turns physics into environmental science, God forbid. But it means that there's nothing fundamental. And it would be very depressing, in fact, for people like me who grew up hoping to explain the fundamental laws of physics. But it may be true, whether we like it or not. And if it is, you see, then when each of these universes comes into being, not only do you get space and time and matter and radiation, but the laws themselves arise in every one of these universes, there's different laws, and all possible laws could reside. So now you got no particles, no radiation, no space, no time, no laws. That's nothing, as far as I'm concerned. Now, the final kind of nothing I have to do because I am wearing this little pin from my late good friend Christopher Hitchens, whose birthday was last week. And I used to talk to him a lot about physics. And he came up with another argument, which I want to present to you in the last two or three minutes. He pointed out that nothing is actually heading straight towards us. So what does he mean by that? Well, the second thing I want to tell you, the first thing is that you're insignificant. The second thing is the future is miserable. Okay, those are the two important takeaway lessons here. Now the reason, who was the first person to show the future is miserable? Well, of course, it was George Orwell a long time ago. He said, to see what is in front of one's nose requires a constant struggle. And this is clearly what he meant by it. What he meant by it was the fact that in a universe full of energy and empty space, it's expanding faster and faster. But that means objects bigger than a certain distance away from us are actually moving away from us faster than the speed of light, which is allowed in general relativity. And because it's accelerating, the longer we wait, the less we'll see. And in fact, in a time frame which you can calculate, about 2 trillion years, all of the galaxies we can now see, except for the ones that bound to us in our local cluster, which will collide together, all of those other galaxies will disappear. And so the rest of the universe is going to disappear, not before our very eyes, but you can ask yourself, what would observers see in the far, far future? So imagine there'll be stars, main sequence stars can live 2 trillion years. There'll be organic materials and water and sunlight, and so the life will evolve, and there'll be civilizations that will discover quantum mechanics and electromagnetism and general relativity. They'll build telescopes, and they'll look out, and what will they see with their telescopes? They'll look out and discover the universe we thought we lived in 100 years ago. They'll look out and see a single galaxy surrounded by an eternal empty space. All evidence of the Big Bang will have disappeared. All evidence that there was ever a Big Bang will have disappeared. But then those stars will die out, and the universe will become cold and dark and empty. And then, as Christopher said, the answer to the question, why is there something rather than nothing, is really quite simple. Just wait, there won't be for long. And that, I think, is a really important way to end, in a sense, because it demonstrates our cosmic hubris. We think we're the pinnacles of evolution, that evolution was designed for us in some way, but of course it wasn't. Similarly, we think that the universe is the way it is now, and it will always be that way. In the far future, it'll be quite different. And so, let me conclude. Science has demonstrated that not only is a universe from nothing plausible, but I would argue quite likely. But more importantly than that, what we mean by something and nothing has completely changed from the time the classical philosophers and theologians first raised the issue. That's okay. Changing what we mean by things is called learning. It doesn't happen in theology, but it happens in scholarship. And that's fine. We have learned that nothing is quite different than we thought, and so something. And what we've really learned, it seems to me, is that the real important question is not a why question. Why questions are meaningless. Because why questions, we don't really mean why when we ask why. Why questions presume purpose. You presume the answer before you ask the question. What we really mean is how. And everyone who's had kids knows that, the infinite number of why questions, the only answer is because, go to bed. Okay? The really, really important question is how, because that doesn't presume purpose. And the important questions, therefore, is not why is there something rather than nothing, but how did the universe evolve, and how can we find out? And that's what science is continuing to tell us. And I think what I'll show with this brief picture at the end to remind you the two lessons I've given you. You're insignificant, the future is miserable, but you should be happy because we are here at this random time in the middle of nowhere, and we've been able to discover the history of the universe back to the earliest moments of the Big Bang, discover 400 billion galaxies, because we are fortunate enough to have evolved with an intelligence. And so instead of being depressed about a miserable future and being insignificant, we should enjoy our brief moment in the sun. Thank you very much. Yep.
My name is Keith Gaddis. I'm a ecologist visiting from UCLA. It's not directly on topic, but it has to do with the general topic here. Richard Dawkins has been advocating for this coming out movement for atheists. And myself as a scientist, I feel this issue is a bit more difficult as it is our duty to remain unbiased in our research. And especially in this country where there is an underlying suspicion by the religious right that atheists and scientists are in some nefarious pact together to conjure up results to support their worldview. As a scientist, does proclaiming oneself an atheist not undermine our battle for science, literacy, and education by giving more fuel to the right of an underlying bias or objective of science?
Okay, well, look, I'm sympathetic to some of what you said, but if you think about it, I think you'll think you realize it's ridiculous. Because if you're a scientist and you came out, would you say it's unfair for a scientist to come out as a Catholic? For Francis Collins to proclaim his religious belief, or for a Nobel Prize-winning physicist to proclaim his being proud of being a Christian? Absolutely not. But somehow, saying you're an atheist is an offensive thing. And in that sense, I completely agree with Richard that we should have a society where you are not penalized for just simply asking the question or saying that the evidence suggests to you that you don't see any need for a creator. But we don't live in such a society. And I was just telling some students today, it's rather interesting. A study was done by psychologists in Canada and the United States about a year and a half ago of college students and adults asking for trust, what groups they trust. And atheists were trusted the least. Actually, they're not the least. They were right alongside rapists. Okay? So when you live in a society like that, what you have to do, there have to be people, I think, who point out that simply asking the question or claiming their point of view is not evil. And as long as we're afraid to do that because we think it's going to offend people, well, that will persist. It's like being afraid to say, during the suffragette period, that women have the right to vote. Because, you'll be just... The point is, we should feel free, and as I say in the movie very clearly, nothing should be above ridicule. Ridicule, as you will have noticed from my lecture, is very important. Satire and ridicule are one way of getting people to think. And so I think it's very important to point out that nothing is above ridicule. If we can ridicule politics and sex, we can certainly ridicule religion. And we have to... so I've had this debate with Richard for many years early on. And I don't think you have to push it in people's faces. And in fact, when I go on Fox News, as I've done in moments when I've been drinking too much, I point out that, and the only thing I could ever get across without being yelled at is you don't have to be an atheist to believe in evolution. You certainly don't have to be an atheist to believe in the Big Bang, because you don't. Empirical evidences, there are a lot of scientists I know who are religious. Okay? So it's fine to say that, and I think it's important to point that out because people are being told the opposite. People are being told in classrooms all around, and in churches in particular, all around the country, that to accept the fact of evolution makes you an atheist. So it's really important for us to tell people that's not the case. But at the same time, it seems to me we have to, my first slide, I'm sorry, you pushed a button. And this may offend some people in the room, but I don't care. I was disgusted this morning again when I was working out and had to see the preacher-in-chief had to come and do a interfaith service here. Why, at every time there's a national tragedy, do we have to suddenly, immediately, do that? We should come together and mourn and grieve and share our common humanity and try and care for each other, but why do we have to do it in prayer? It's offensive to me. And we should realize it isn't a given. And unless some people speak up and say it doesn't have to be a given, then it's always going to remain that way. Okay, that's my little speech. Okay.
Professor Krauss, my name's Tony Kahn. I'm not a scientist, and my head is spinning. So thank you for that.
I achieved my goal. Okay.
But one thought started to form in my mind as you were saying, about 1 trillion years or so from now, we'll no longer have any evidence of what we now know to be true.
Yeah, and you're going to say, what about now, right?
No.
Oh,
I'm wondering if there is, however, a record 1 trillion years from now that we knew these things, but it's really only hearsay because we no longer can prove it. What's the future of the scientific method?
Well, look, I mean, that was my point. I think subtly what I was trying to suggest is that falsifiable science can lead to false results. We are, and I've written about this extensively, and it's an area of, in some sense, my own research. We are an embarrassment of riches. We are at the point of asking questions in cosmology that we wouldn't have thought of asking 40 years ago because of the amazing discoveries we made about the universe. But it immediately gives the limits of science. Because we live in one universe, again, most of us. And that means that we're forever limited in the knowledge we have. For example, if there's a multiverse, we may not know about it directly. I would argue there are inferences you could make that there are many universes without knowing it directly. But we are limited by that fact. And that means there are limitations to the empirical method because we live in a single universe. And it should also give us some cosmic humility. Because if there are things we can't see 2 trillion years from now, we should realize that although we have this interesting picture of the universe that all holds together, that there may be important observables that we can't see now that are essential. That had we been smart enough to evolve 5 billion years earlier may have been observable, or maybe 100 billion years from now may be observable. So we should realize that we shouldn't assume we know everything. And as I say, the good news is we live in a very special time. The only time when we can observationally verify that we live in a very special time. And by that I'm facetious. I really mean that we have to realize that there are limitations to empirical science. And it could be that in the far future, there are some things that are not falsifiable. That we say, well, look, it walks like a duck and quacks like a duck. It's probably a duck, but we can't prove it isn't a duck. And we may just have to accept that fact because we're stuck in one universe. Yeah?
Thank you, Professor Krauss. Rodrigo Martinez. I live in the design world, and part of what we try to do is design for serendipity, whatever that means. And I'm probably thinking about it differently after today's talk, so thank you for that. So if I can push you to imagine whatever version of humans or whatever we are, I don't know, 5,000, 10,000 years from now, what do you think are going to be the fields or areas that influence the thinking of people like you 5,000 years from now that create this was really unexpected. Now we know why that was like that. Where do you think those fields or those areas have come from?
The great answer to that is I don't know. And that's what makes it so neat. Because I don't know what the people are going to be awed about in a year. That's why I do science. The great thing is, when I have to write grant proposal, you always lie and say what you'll be doing 3 years in the future. But you don't, if it's an interesting field, you don't have the slightest idea. And that's what's great. Nature keeps surprising us. And people tell me, what's the next big thing? I say, if I knew, I'd be doing it. Okay? So what we need to do is we need to keep on exploring the universe. And it will keep on surprising us. And my hope is that what people are thinking about in 5,000 years is well beyond anything I can imagine. And I would be very surprised if that weren't the case. but not because of their imagination, because of the universe. If we locked physicists in a room without windows and asked them 10,000 years what the picture of the universe would be, we'd ask a woman physicist and she'd come out and she'd give a picture, and it would be not at all related to the real universe. All of us would have been that way. We need experiment and observation. And if we stop doing that, sad. Okay. Last question.
Professor Krauss, it's an honor to see you.
Thank you. It's an
I
honor
was
to-
I was recently watching that debate where you protested the segregation by sex.
Yeah.
Yeah. You won. Yeah. You. I
Well,
understand.
other people there, many of them didn't think I did, but
But
especially the women who were segregated were the maddest at me of anyone.
That's
when
what I
unsegregated that
heard.
event.
But your opponent was arguing that infinity doesn't exist, and so you.
No, I said infinity. No, the other guy said infinity can't exist. It's not a physical quantity.
Exactly. He was arguing that it doesn't exist, and you pointed out many situations in which it does. And I believe that you said that the sum of an infinite series is -112.
Oh, yeah.
Now, I couldn't find anything about that online, so I was wondering
It's
if
called
I
the Riemann
emailed
zeta
you.
function.
What's that?
It is a true and ridiculous fact about mathematics. I'd love to give a whole riff on infinity. Again, I wrote about it a lot in the book, but this is an amazing fact. If you take the series 1 plus 2 plus 3 plus 4 plus 5 plus 6 to infinity, what's the sum? Well, of course, it's infinite, but mathematicians can summing an infinite series is very ambiguous. So you can define a set of rules that give that make self-consistent things that sum that series. And you can do it, and there's a whole way of doing it. It involves anyway. And it turns out the self-consistent number assigned to that series is called the Riemann zeta function of argument -1, I think, is that sum of that series, 1 plus 2 plus 3 plus 4 plus 5, all the way to infinity is -112, which is an amazing result because no term is negative and every term is bigger than -112, which shows, of course, how weird mathematicians are. But this is not just a matter of academic interest, because it turns out to be a central facet of string theory. It turns out that the original string theory had to be in 26 dimensions, specifically because you wanted to avoid infinities. And you could show that two terms would cancel and give 0 if you had this infinite series and it added up to -112. So people take these things seriously. And it just means that we need to be able to, it just means that we're uncomfortable. And being uncomfortable with infinity is a good thing. I guess I want to close. I think I may have even said it in the Krista Tippett thing. I did, I remember. One of the purposes of science, it seems to me, is to make us uncomfortable. Because that requires us to rethink our place in the cosmos.